All right, welcome to today's class. Today we'll continue to talk about ggplot2. And tomorrow I will talk about the last part of ggplot2 and give you 45 minutes to work on your quiz. All right, let's start. So first, let's load the tidyverse package again. Tidyverse is a collection of packages, including ggplot2, this package. So first, take a look at these two plots. So these two plots are using the same data set, the MPG data set, and exactly the same mapping. You see, the X and Y coordinates are exactly the same. Okay? However, they look very different, right? So the main difference is because they use different gems. Right? The first one use gem point. The second one use gem smooth. Okay? So a gem is the geometric object that the plot uses to represent data. Okay? So if you choose to use different gem or geometric objects, you definitely will see different plots. Okay? The left one is a scatter plot. The right one shows you a smooth line, which uses local weighted regression model. So underlying the behind the screen, a model was fitted actually, and the result is a smooth curve. Okay? And this band is a 95% confidence band for the mean response using this smoother. So as I said last time, ggplot2 provides a lot of different gems. For example, if you want to create a bar graph, you can use gem bar, histograms, gem histogram, box plots, scatter plots. Right? So if you want to take a look at a big picture of using ggplot2, you can check the cheat sheet website, data visualization of ggplot2. And this is a PDF version. And on this web page, you can see some details in the cheat sheet, but in larger characters, so easier to read. All right. So ggplot2 allows you to add multiple layers of gems into the same plot, into the same coordinate system. As we learned last time, ggplot function will open a coordinate system, and you can choose to add layers of gems to it. So for example, if we want to overlay this smooth curve on the scatter plot, we can just add another gem to the original one. So we'll first add a layer of point and then add a layer of curve or line. However, if we examine this code, you see some duplication. You see the mappings are exactly the same, right? To avoid this kind of duplication, we can choose to move this mapping into the ggplot function part, as I said last time, right? So move it to the ggplot part. And then you can, we don't need to specify any arguments in the gem part anymore, right? But you still need a pair of parentheses when you call them. And this is a global option, okay, or argument or global mapping. And global mappings will in effect in all of the layers of gems. However, you can choose to override it in local mapping options. For example, we create this so we still choose to put the mapping in ggplot, this part, and then we want to map a categorical variable drive to color for the points only. Then we can add a mapping argument in gem point. Okay, so then you see this plot. You see, we use different colors to display different drive categories. So red is four wheel, and green points are corresponding to front wheel, and blue points are corresponding to rear wheel. Okay. However, you see, since this mapping is local in GM point, it does not have any effect on the curve. So the curve will still have only one curve. So we fit a global curve for all of the points, but we choose to use different colors to show different drive categories. Okay. And apparently, this one is sort of like an extension of the mapping option. It did not override anything because there is no conflict, right, between these two mappings. So it's kind of like an extension. You can also choose to override the global option. If you specify a different X and different Y here, it will work, I believe, or something else. Okay, but it will override the global option. Okay. All right. Next. Of course, we can add local mapping for the smoother too. For example, we can map the drive variable to line types. Then ggplot2 will automatically use different line types for different categories of drive. So you see, this is dotted. Dotted is for front wheel, and the solid line is for fore wheel, and this one is for rear wheel. Okay. And of course, this is not really good because we use sort of different GMs, different visual cues to show the same variable. Right? In the points part, scatter plot part, we map drive to color, but in the line part, we map drive to line type. This is not very consistent. A better option is just directly map drive to color in the global mapping part. Then you see they are more consistent. Okay. And also notice that whenever we map a categorical variable to a visual cue, legends will be provided automatically for us. So this is also, yeah. So this one is also, you see, colors and line types are also shown here in the previous example. All right. And lastly, we can add context to a plot. So notice that if we don't specify anything, then by default, ggplot2 will only provide the minimum amount of context, usually just X and Y axis labels and tick mark labels and legends if necessary. But we can definitely choose to add more context. We use the labs function to add context. You can put a lot of different context in this. Labs stands for labels. Labels. So for example, we can add a title using the title equals function. We can add subtitle. We can also add a caption. The caption will be at the bottom of the plot. So caption is here. And just don't forget to use comma to separate these arguments. And notice that in this plot, I map class to color instead of drive class. Class has 7 categories. But I didn't map class to color in the line plot, like in the smoother plot. And instead, I specify SE equals false. SE stands for standard error. So by default, it is true. So a 95% confidence band will be provided for us automatically. You see 95% confidence band. Right. But if I don't want to show it, I can just set SE equals false. And we can also add X and Y. We can also change X and Y axis labels. So the argument are just X and Y, X equals and Y equals. You see, instead of using the original variable names, we can give a long character string to explain the variable. We can also add the units of each variable to it to make the plot better, in conveying information to your readers. Okay, so you can change X and Y labels. So notice that I still put these in the labs function, okay, or layer. And legends will be provided automatically whenever you map a categorical variable to a visual cue, but you have the option to omit legends. You can just say show that legend equals false, then the legend won't be shown. And these two functions, gem text and gem annotate, can also be used to provide some textual annotations on the plot. So basically, gem text can you can use it to add any text anywhere in your plot. You can just specify the coordinate that you want to add the text and also the sentence or the text you want to add. Right? And annotate similar, right? Perform similarly. So you can add, for example, arrows, some other signs to a plot. All right, now let's move on to the next topic. We'll talk about logarithmic scales. Take a look at this data set, the diamond data set. I think it is built in ggplot2. Okay. So this data set contains information about 54 diamonds, 54,000 pieces of diamond. And the variables are price, carat, which is the weight of each piece of diamond, and color, clarity, and cut of each diamond. Right. So it's a quite big data set with 54,000 observations. Right. So suppose we are interested in the relationship between weight and price of the diamond. I want to know what relationship we have. We can create a two-dimensional bin plot to show the relationship. Right? So start with ggplot, right? Specify the data set and the basic mapping. X is equal to carat, which is the weight, and Y is equal to the price. Right? And then add a layer of two-dimensional bin plot. So two-dimensional bin plot is a variation of scatter plot. So instead of showing each observations using points, it will separate the entire data, the two-dimensional plane into grids, okay, somehow like this. So for our data set, it will separate the coordinate system into equidistance, not necessarily squares, like rectangles, right, with the same size. And then it will count how many observations in each cell. And then use color saturation to show the quantity. So for example, you see from the legend, we can see that the larger the count, the lighter the color, which is a little bit counterintuitive, but ggplot2 just is designed in this way. Okay, the larger the value, the lighter the color saturation. So basically, for each rectangle, it will show the count. Right? So see, this one is the lightest. Right? This cell is the lightest, which means there are most number of observations in this cell. Right? All right. So this is a two-dimensional beam plot. It's a good way to show relationship between two quantitative variables if there are too many observations. If you create a scatter plot, you will see a very dark cloud of points. It's very difficult to see the density, which part has more observations, which part has fewer observations. But this one is a good way to show large data set. Anyway, from this beam plot, you can see that there is a positive relationship between caret and price. However, it may not be a linear relationship, right? You see somehow like a curvy relationship. And also you see that the variation increases as the magnitude of X and Y increases. So this is a sign that the data are kind of skewed. So let's try to take log 10 of both X and Y and then recreate the beam plot. So we can directly apply the log 10 function on both weight and price and create a plot. So now it looks very linear, right? And the spread does not change anymore. So you don't have, if you fit a regression model, linear regression model, you won't need to worry about the constant variance assumption anymore because the variance, stays similar. So very good transformation. However, in this graphical display, you see that the X and Y variables, the tick mark labels are corresponding to the log transform data. So you see negative 0.4, 0.4, 0.8. So they are not very intuitive anymore, difficult to understand and interpret, right? Because they are corresponding to the log of the original values. So negative 0.4 is actually just 10 to the negative 0.4, okay? And it's definitely a positive number, but it is shown in the log scale, log caret. So a better option is to use logarithmic scale. Okay? So instead of transforming the data manually, we can keep them as their original forms. And instead, we add these two lines, scale X log 10, scale Y log 10. Then you see still the data is sort of transformed still. I use log 10, but actually the X and Y the XY axes still show the original values of X and Y. You see positive values, right? The original values. Although you see the increase in a nonlinear way, in an exponential way. So this is a better practice in visualization. Use logarithmic scale. Alternatively, we can use these two functions, scale X continuous and scale Y continuous. And with transform, trans equals log 10 and trans equals log 10. So these two are more flexible than the previous one. The previous one are only good for log 10, but these two are good for many different transformations. For example, you can use natural log by specifying quote log. You can take square root or you square it. So there are many more options. So this is an alternative way to use logarithmic scale. All right. Now let's talk a little bit more about color scales. So as we have learned last time, this R-Color Brewer package provides some colorblind safe palettes in a variety of hues or groups, right? So let's take a look at the plot. So in the first plot, we use regular color option, the default color option. We map drive to color. So for normal people, it's okay, but you see the contrast between among colors is not very obvious. We can choose to use colorblind palettes, right, by specifying this scale color brewer, right? Don't forget to add a plus at the end of the last layer. Right? So we use this to connect the different layers of code. Right? And we can use use set one. Remember, set one is one of the qualitative palettes, which is used for qualitative variables, categorical variables. So you see, apparently now these three groups look more different in colors, much more different. Okay, so this is kind of colorblind safe. All right. Let's examine this scatter plot again. So this is the original scatter plot between displacement and highway. So can you tell that this plot actually only has 126 points? Okay. But the data set, MPG data set, actually has 234 observations. So it turns out that because of rounding, the data are kind of coded in grades. So there are a lot of repeated values. And consequently, each point in the plot may represent multiple points. They overlap with each other a lot. So from this scatter plot, you cannot tell the density or the mass of points, right? So one way to resolve this problem is to add an argument called position equals jitter. If you specify this argument, then ggplot2 will automatically add a small error to the coordinates, to x and y at the same time. So it's kind of jitter a little bit. Then after that, you can see the true, sort of not exactly true, but you can see the sort of the density of observations in the scatter plot. For example, there are more observations over here than over here. From the previous plot, you cannot tell any difference in density. In this plot, it's more obvious. And because this is a very useful operation, ggplot2 also provide a function called GM jitter. So this is exactly the same with this GM point with position equals jitter. To be honest, a better practice or better choice is to change the transparency level of the points by setting the transparency parameter alpha. For example, if by default is equal to 1, so all of the points are 100% solid. If you set it to be, for example, 0.5, then you can tell the difference. If there are more observations on one point, then it will look darker. And if there is only one point there, it will be lighter. That's only 50% of the solid shade. Right? So that will be a better, I think that'll be a better option because you will not twist your data. Right. All right. Any questions so far? So now let's move on to the last session. We talked about, so now in this section, we will talk about coordinate systems, a few examples of different coordinate systems, and lastly, statistical graphical displays. Ultimately, the goal of graphical display is to understand your data, to explore your data. But for different data types, we should use different graphical displays, and different combinations of data types require different types of graphs. So in this part, we'll talk about different cases. So first, take a look at coordinate systems. In ggplot2, there are 3 of them. By default, Cartition system. We also have map system and polar system. So for Cartesian system, you have the option to flip the axis. For example, we create, so now in this, we still use the MPG data set. We want to create a box plot for highway fuel efficiency, highway MPG. And we want to compare the highway fuel efficiency among different classes of cars. Okay? Then we can let X be class, Y be highway, and then create a box plot. So it will be a side-by-side box plot. You can compare the distribution of highway fuel efficiency among different classes. Apparently, so these two, compact and mid-size, have relatively the highest highway fuel efficiency. If we use median as the standard, and median is the bar, right? And we can also see that this subcompact has the largest spread, etc. If we only have a few categories in the categorical variable, then this vertical box plot is okay. But what if we have like 20 categories, 30 categories, okay? Then it might not be very convenient to use a vertical box plot. In this case, we can choose to flip the coordinate system. Just add a line, pull out flip. Then you see we have this plot. Right? Everything. So X becomes Y, Y becomes X. So notice that in this chunk of code, I first save the result of this box plot in G, as a G, and then I type G with this. And then take G and add this coord flip function, you can flip it. Right. I didn't save the result, by the way. G is still like this, okay? But you can twist it a little bit. And also, if sometimes the X tick mark labels are very long, suppose you have very long text strings for each class, then it will be better to use a horizontal box plot, because then you have more space for each tick mark label. It will be easier. All right, so this is for Cartesian system. You can flip the X and Y axes. And next, let's see an example of map coordinate system. Again, our class is not focused on geographic data, like spatial data. So we will just use one example to see the importance of using the correct map system for this geographic data, right? Geographic data. So let's see, we will load this package called maps. So this one contains some information about different countries and counties in the world. In the US, we have county data, geographic county data. So let's load the data about New Zealand. So this map data function is contained in this maps package. And call it NZ. And then let's first create a regular polygon plot. A geometric GM polygon will create a polygon plot somehow like this. Right? X is longitude, Y is latitude, and group equals group. So this group is a categorical variable which defines a small unit of data. The unit maybe is about an island, or yeah, it's a kind of an area of observations. And then add a layer of GM polygon, and fill is white and color is black. So we have this. Right? So this is how it looks like the map of New Zealand looks like if we use the regular Cartesian system. Right? However, if we use the correct coordinate system, which is the map system, it looks like this. Right? So you see the difference between these two. So this is the correct look of New Zealand. This is not the correct look. Okay, it's expanded and twisted. So this example shows you that it's very important to use a map system for geographic data. All right, next one is polar system. Yeah, again, in the polar system, we also use two coordinates to show the position of a point. So there are two coordinates. The first one is called the radial coordinate or simply radius. So for example, for this red point, the radius is this, the length of this. Right? And the other one is called angular coordinate or just polar angle. So this is the angular coordinate. And then let's see how to create a pie chart using ggplot2. Notice that ggplot2 does not have a specific gem for pie charts, right? I don't know why. Probably the author doesn't like pie charts at all. So there is no function corresponding to pie chart directly. However, you can create a pie chart using a bar graph, transform bar graph. So let's first do something that's, we would use a data set called empty cars. So this is a built-in data set in R. You don't need to load it or import it or download it. So we first will convert cylinder to a factor because we will use it to create to separate the data. We'll create a bar graph for cylinder. It was coded as a numeric variable. But I want to treat it as a factor. And then we first create a bar graph. X is equal to cylinder and fill equals cylinder. And create a bar graph. We have this. This is not necessary for a regular bar graph because we have X tick mark labels. We can differentiate these three categories. Right? However, this will make it look better. We'll use different colors to show different categories. Right? So this is a basic bar graph. Right? Then the next step is to change some arguments. Let X be 1, the factor of 1. Right? Somehow like this. It's a 1. Right? So 1 value for X. And then fill equals cylinder. So this will actually map cylinder categories to different colors in the same bar. So this is a result. Right? You have 1 bar with 3 colors. Right? And of course, the height of each part is corresponding to the proportion of each category. Right? So it's a stacked bar graph. And also gem bar width equals 1. So the width of this bar is 1. This is the intermediate result. Okay. And finally, we will add a coordinate polar. Right? So we will, instead of using, so by default is a Cartition system, right? But you can add this to change it to a polar system. And theta equals 1. This theta is corresponding to the angular coordinate in the polar system, and we map y to theta. What is y? Y in this plot is, you see, originally is corresponding to the height of the bar. Consequently, in this case, it's corresponding to the height of each part of the bar, the category proportions, right? And then we omit the X and Y labels, omit them, because in the polar system, it doesn't make sense to use the original labels anymore. And then we have this result. So it's a pie chart, right? Quite a lot of work. And there is a pie chart function in base R, right? But it's very basic. It does not look very nice. And that we will see another way to create a pie chart a little later today too. Um, anyway, this is a way, and this is how we change the coordinate system. Just add this, like coord underscore polar. Change it. All right. Now let's move on to statistical graphical displays. So this slide shows you a big picture of the class that for different variables and different combination of variables. Okay. For one continuous numerical variable, we can create a histogram, a density plot, box plot, and QQ plot, and area and frequency polygon. Okay. And in particular, QQ plot is used to check the distribution of some sample data. So it's kind of special in this group. For one categorical variable or one discrete numerical variable, we can use a bar graph, a pie chart, or Cox-Com plot. So this is a variation of a pie chart. And for two numerical variables, we are interested in the relationship, usually, right? So we can use a scatter plot or a contour plot. So this one will show the joint distribution of the two numeric variables, and also two-dimensional beam plot. We have seen this in the diamond example, right? We use color shade saturation to show the density, right? So that is actually a three-dimensional plot. The third dimension is shown using the color saturation. And then two categorical variables, we can use a tile plot. Tile plot is very similar to two-dimensional beam plot. So actually in ggplot2, you can use these for both cases actually. And the next one is stacked or dodged bar graphs. And last one is count plots. And the last group is one categorical and one numeric. So basically grouped numeric data. So you want to examine the relationship between one categorical variable and one numeric variable. We can use side-by-side box plots. We have seen this already. And we can create a violin plot. So violin plots are similar to side-by-side box plots, except for we use a violin shape for each category of data. And last one is frequency polygon. All right, let's start from the first group, the one numerical variables. We definitely can create a histogram. Whenever you have any numeric variable, the first action probably is to create a histogram to check the overall distribution of the sample data. So we can use the ggplot function to create a histogram. Right? So notice that I use a data set called SAT 2010. So this one contains some information about SAT scores in 2010. There are some different scores. One of them is the math score. So notice that I save this in G. Right? G is just a coordinate system with the data stored and also the x variable specified. Right? No gems yet. Okay? No geometric object specified yet. Okay? And then I add a layer of histogram. Okay? And then you see this is so this line print out this plot, create this plot. So this is a raw look of the histogram using ggplot2. Right? It's not really good because even there is no borders for each bar even. Right? And also automatically this message is printed for you. Right? Start bin using bin equals 30. So this is a default number of bins that is used for our data, 30 bins. you can choose to change, you can change it. Okay? For example, if you think there are too many bins, you can change it to 20 or 15, etc. You can also change the bin width. Okay? Essentially, you can just, if you have larger bin width, then apparently fewer number of bins. And the second plot, I still take G and then add a layer of density curve. So this one is showing the empirical density curve using kernel smoother. So it will show you the pattern of the distribution. So density curves, empirical density curves are also useful for showing the distribution of numerical variables. And as we have learned, we can change the number of bins. For example, we can use fewer bins, so 15 bins, then it looks like this. And we can also change the bandwidth in the density curve. So if bandwidth equals 5, you see some more patterns in it compared to the previous one. See, no detail at all in this one. But if you change bandwidth equals 5, right, basically we use a smaller bandwidth. So we have this. So for more details, you can type question mark the function name to see it. Of course, you need to first load tidyverse package, and then you can tap this to see the documents of these two functions. Yeah. So for all ggplot2 functions, these parameters have some sort of optimal values, right, calculated for your data. If you omit these arguments, the function will choose the optimal number of bins, optimal bandwidth for you. You can change it. So namely, for different data sets, the optimal number of bins and bandwidth might be different. Pay attention to that. And you can also overlay an empirical density curve over your histogram. Just pay attention that you see from these two plots, the y-axis for the histogram by default is corresponding to the count, right? Bin count, the number of observations in each bin, right? So it's on an integer scale, but the empirical density curve, you see they are kind of like proportions or probabilities, right? They are definitely on different scales. They don't match, right? So if you want to overlay an empirical density curve on a histogram, make sure that you let them have the same scale for the y-axis. So that's why to create this plot, I let y equals density. But in ggplot2, you have to use this kind of syntax after underscore stat, parentheses density. So what is after stat? So this is a statistic that is calculated during the process. Okay, it is stored in the background somewhere. Okay, you can extract them by calling this after underscore stat and density. There are other options, for example, count or proportion. Okay? But if we want to make the histogram and the empirical density curve exactly match with each other, we should use density. Okay? And then we can have this plot. And notice that there are some other functions, other arguments you can use to make your plot look better, right? To improve your plot. For example, I can change the color of the bars using the fill argument, not color. Right? The color argument will change the border color and not the inside of it. And color is the border color, and make it white so that we can see they are separated. And then alpha is used to adjust the transparency level of the bars. Okay, so usually, if you put the histogram in the background, you want to make it lighter. So that's why alpha equals 0.5. It's 50% of the solid color. Okay. And then bins is the number of bins. Okay. So these are local options in histogram. And then for the density curve, I specify the bandwidth and also the color of the curve, hollow, and then line width, and make it more make it thicker. Okay. So these are all available, and there are many more arguments available for you to fine tune your plot. But I just showed you some examples of tuning your plot. So we're done with histograms and density curves. Okay, they usually go together. And we can also create box plots for numerical variables, of course. And ggplot2 also has this gmbox function. So we have seen this before. We created a side-by-side box plot. But for one numeric variable, we can also do it. So as you know, the box plot will show you the 5-number summary, right? The minimum, the maximum, the minimum, the maximum, first quartile, third quartile, and the median. So you can compare the plot with the 5-number summary we calculated using the quantile function. Okay, by the way, the quantile function in base R will, by default, calculate the 5-number summary for you. Okay? And you also have the option to specify a particular probability. For example, if you add 0.99 in it, then it will calculate the 99th quantile. Okay? Anyway, this is a very basic box plot. Okay? And next is QQ plot. QQ plots are quantile plots. Okay? They are used to check the distribution of your sample data. Okay? So after you collect some data, you're not sure if the data set follows a distribution or not, for example, normal or not. Okay? So the QQ plot will help you to check it. The ggplot2 also has this gmqqq function to help you to create a QQ plot. So it's basically a scatter plot. A scatter plot of what? Of your sample data and the theoretical quantiles of your sample data based on normal distribution. So let me briefly explain this to you because I think some of you are familiar with the underlying theory of QQ plot, some might not. Okay, so let me just briefly explain it. So suppose you have a very small sample with 5 numbers. One, if you order them, they are 1, 5, 15, 20, and 30. Okay, 5 numbers. Okay. Then what are their theoretical so what percentile they are? Okay. So if we, roughly speaking, 1 is the smallest. Okay, we can say it is the 20th percentile. Let's just think in this way. And 5 is the 40th percentile, and 15 is the 60s, and 80s, and 100. Right? Because for 1, there are 20% of observations that are smaller than or equal to 1 in our small data set, right? So 1 is the 20th percentile in that sense. and 30 is the largest, which is 100 percentile. All of the observations are smaller than this. Okay. And the QQ plot function will find the 20th percentile for a normal distribution with mean and standard deviation that are same with your sample data. Okay. So it will calculate the sample mean and sample standard deviation for your data set and find the theoretical quantiles of a normal distribution with mean equals x bar and standard deviation of s. Okay, so let's just call them x1, x2, x3, x4, x5. Okay, and then create a scatter plot for your sample data and the theoretical quantiles. Okay, and so if your data is from a normal distribution, then what will we expect to see? We'll see a straight line relationship, right? So that is because you see, yeah. So you all know, so we all know about the relationship between standard normal and the normal, right? So suppose Z follows a normal distribution with mean 0 and standard deviation 1, and X is also a normal random variable with mean mu and standard deviation sigma. Then we can standardize X by subtracting the mean and divide it by the standard deviation, and is equal to Z. And now it's standard normal now, right? If you reverse the process, we can easily find that X is equal to mu plus Z times sigma, right? So X and Z should have a linear relationship, right? If both of them are normal. Z is normal, standard normal, X is somehow normal, y is a normal random variable too. There is a linear relationship. Okay. And go back to our small example. So actually in the QQ plot, if you examine the x-axis label, the tick mark labels, you have -2, -1, 0, 1, 2. So apparently these normal theoretical quantiles are corresponding to standard normal. So basically, you will create, so the QQ plot function will create a scatter plot between your sample data and theoretical Z values, Z scores. Right? And if your data is from a normal distribution, right, then they are somehow like these axes, right? And the x-axis are these Z values. Right? If your data is actually normal, then you should observe a straight line relationship. Right? No matter what the intercept and slope are, right? We don't care about the intercept and the slope. They are the mean and standard deviation of your data. Right? But it has to be a straight line. If your data is from normal, it has to be, roughly speaking, a straight line. So that is a whole theory about it. If you observe a scatter plot that is kind of like a straight line, show a straight line relationship, then your data is from a normal distribution. Otherwise, not normal. Right? So now let's see how to create it. So notice that we first add this GMQQ. By default, it will compare your sample data with normal distribution. Okay? However, you have the option to compare your data with other distributions like F distribution, T distribution, chi-square distribution, etc. You just need to specify one more argument. Okay? They are available, but by default, it will compare with normal, which is the most common case. Okay? And then we can also add a reference line using this QQ line. So this will add this straight line. Okay? So assuming there is a linear relationship, so this is a straight line relationship between 1 and x. right? We can compare the scatter plot, the QQ plot, with the reference line. Right? And you also can change the color of line, the color of points, and also transparency. So all of them are like universal arguments you can use to change visual cues. Right? And I also added X and Y labels to the QQ plot, and also the last line theme aspect dot ratio equals 1 will make it a square shape plot. Right? By default, it's a rectangular shape. All right. Yeah. You might wonder why don't we just put GMQQ line first and then GMQQ. That's because I think only if you put it later, you can change the labels of X and Y. GMQQ has its default X and Y labels, and you cannot change it. You cannot change them. All right, this is all about QQ plot. I think it's a useful tool in data exploration. So I spent some time on this. All right. Any questions so far? Now, next type of data, one categorical variable. We can create a bar graph. So in this example, we will use a new data set, each called help RCT. Is in this package, Mosaic Data Package. So HELP RCT stands for Health Evaluation and Linkage to Primary Care. It contains some data about people who use substances like drugs and their health situation. And so there is one variable called homeless. And homeless is the variable name, and it has two categories, homeless and housed. So one category is also called homeless. We can create a small distribution table for this variable. So we can use this with function, with data set, and then apply a function on a variable, create a table. So these many homeless observations, these many housed individuals in the data set. And then we can create a bar graph to show the distribution of homeless, this variable. So notice that we let X be homeless and let Phil be homeless too, and add a layer of bar. See, this is a very basic bar graph. If you omit Phil equals, then it will just, both bars will be gray. It will be in gray color. Anyway, this is a distribution of homeless, a very simple bar graph. And there are ways to tweak your bar graphs. For example, let's take a look at the diamond data set again. Suppose we want to create a bar graph for cut. Cut has 5 categories: fair, good, very good, premium, and ideal. 5 categories. It is an ordinal variable. So let's create a bar graph for it. So instead of using the count, so see by default, the y variable is corresponding to the count frequency. You have the option to use proportion instead. Similar to the histogram, in the histogram example, we can let y be the after stat of proportion, right? And then you see the y-axis is used to show the category proportions. And pay attention that we need to add this argument, group equals 1. Why do we need this? It is because by default, group is equal to the x variable. So in this case, it's equal to cut. Okay. Then if we group the data by cut and then calculate the category proportion, then each category will have 100% proportion, right? Because you already separate them and then you calculate the proportion of that category, definitely 100%. Okay? So if you omit group equals 1, you will have a plot like this. Okay? All categories have 100% proportion, which is useless, meaningless. And so you have to specify group equals 1, right? To override the default option, which is group equals cut. Group equals the X variable. Right? And you can also change the color of the bars to still blue. So this is one way to adjust the bar graph. So usually we want to show proportions instead of counts. And we can also specify the y-axis manually. We calculate the proportions manually. For example, we can let y be after stat count divided by sum of after stat count. So basically ni divided by n. So that is definitely the proportion. So of course we have after stat proportion. We don't have to do this, but this example just shows you some other possibilities. So in a bar graph, you have the option to specify how the y variable is defined. Right? You can use any quantity. Right? You can calculate by yourself. Right? As long as the quantity is available in the after stat group. Right? All right. Next. Yeah. So by default, the stat argument in GMBar is the count. Is a count. If you don't specify the y variable, then stat will be the count. For example, in the very beginning, you see I didn't specify y, right? I only specified x. And the count is calculated automatically for us. And the counts are used to show the height of bar. It is used to define the height of bars, right? So that is underlying stat. Okay. Equals count by default, okay, for bar graphs and also for histogram. And you can change this default behavior. For example, suppose I don't have raw data. I have a summarized table like this. Okay. So 2 columns, cut, category, and the frequency. So since frequency is already available for us, we don't need to calculate it anymore. Okay. So in this case, you see the data set is demo. X is cut. Okay. Ignore this first, read other thing first. Okay. X is cut, and y is equal to the other variable frequency. Okay. So this is x, this is y. Okay. And because we already have those calculated frequencies in this table in our data, we don't need the program to calculate the count for each bar and for each group of x anymore. Okay. So we need to specify stat equals identity, which means it will be just the y variable we specified. And then we'll have this plot. Okay. And what about this? So this one give you the option to order your bars according to some quantity. For example, I ordered the bars, the cut variable, by the frequency, by default in ascending order, from the lowest frequency to the highest frequency. And then we have this result. So this example shows us that if we have summarized data, like summary table, and we already have some value we know we will use to define the height of each bar, then we need to specify that equals identity to avoid counting the frequency for each category. If you don't specify that, then the count will be equal to 1 for each category, apparently. Right? And all the bars will have the same height, I think. All right. Alternative way to create bar graphs. You can also use this GM column to create the same plot. So GM column and GM bar are kind of parallel in ggplot2. They're essentially the same thing, but GM column it focuses on the counts of each column somehow. But you can use it to create a bar graph. So, all right. Next, Cox-Com chart. So this is a variation of the bar graph and also similar to pie chart because it uses the polar system. Right? So let's take a look at this example. So we will create a plot for cut again. Right? To create a Cox-Com chart, we will first create a bar graph. Right? But this is not a traditional bar graph because notice that there is no space between any two bars. Right? For regular bar graphs, there is some space between any two bars, right? To show that the categories are not continuous and it's not like in a histogram, all the bars are together, right? No space. But in bar graphs, there should be some space in between any two bars. Right? So let's see what we did. So X equals cut, fill equals cut. So make them have different colors. Okay? And then width equals 1. So this will, I think this will get rid of the space in between any two bars, right? So get rid of the space. Because in the final product, we don't want to have any space in between the slices, right? So that's why we get rid of the space. And then this part will make it a square shape, right? And get rid of the labels of X and Y. And also get rid of the legends. Right? So by default, it will print out some legend here. Right? And then save the result in bar. So bar looks like this. Sort of similar to a regular bar graph. And then just need to add co-odd polar. Yeah. And then you see this kind of, so we get this plot. And we change the system from Cartesian to a polar system. So it's kind of a combination of a bar graph and a pie chart. Yeah. However, it is different from a pie chart. Can you tell what's the difference between this plot and the pie chart? Anybody?
In a pie chart, it's the proportion of the circle is the value that we're looking at, and here it seems to be like the size of the triangle or the radius.
Exactly. Thanks. Yeah. They actually use different visual cues or quantities to demonstrate the data, right? In the pie chart, we use angle to show the proportion of each category. But the radius stays the same for each slice, each category. But in the Cox-Com chart, the angles are the same, actually. If there are 5 categories, so each one the angle will be 360 divided by 5. They all have the same angles. However, the radius are different. We use radius to show the proportion of each slice, each category. Right? The radius is corresponding to the height of the bar. So that's why right? It's kind of a variation of the bar graph and also the pie chart. Right. Yeah. Lastly, a pie chart. As I said, we can actually create a pie chart using base R functions. And let's see. Yeah. Yeah, this one actually still uses a ggplot function. So we first summarize the data. Suppose we want to create a pie chart for cut again. So we create a little data frame. So first create a table. I call it cut table. And then use the data.frame function to convert it to a data frame. And also we add column names. So this is the data frame we have. Two columns, cut and count. And then let's create a pie chart using ggplot2 again. But now we're not dealing with raw data. We are using a summarized table. So specify the data set, the data frame, cut df, right? And specify the mapping x equals nothing, right? Only y variable, right? Which is the count, and fill is equal to cut. So then, so this is basically gym bar, same thing, with width equals 1. So this part will stack all of the categories in one bar, and then use a polar system, right? And the theta equals y. Theta is the angle. And then we'll create this plot. We can also fine tune this plot. So this is G, a basic bar pie chart. We can adjust it a little bit more to make it look better and add more information. So you see by default, the counts are outside of the circle. Right? And we also have X and Y labels, which are not necessary. So we can first do this plus CM void. So this will, I think this will get rid of the background color. And then add some text using GM text function. So label equals count. So this will, so these are the labels, right? The count will be used to label each slice in the pie chart. And position equals position stack, vertical adjust equals 0.5. This means I will put them in 50% of the radius, right? So this is the whole radius is about 50% of the radius. So in the middle of the slice. And then get rid of the X label, the Y label, and the fill equals no. Yeah, I'm not sure what this is about. And lastly, use set2. Okay. In color brewer, set2 is the second qualitative palette in the second group for qualitative variables. So it looks nicer than the original one. I think the colors look better. And you add some details. Apparently, you can do something else. For example, add proportions instead of count into the slice. Anyway, it's quite difficult to create a pie chart using ggplot2. And you probably need to use a lot of code to create a pie chart. All right, I think we can stop here. And tomorrow we'll finish the rest of the slides.